Hello, everyone, and welcome to the third episode of the From Alchemy to Atoms podcast. I am your host, Dave Johnson. As I just mentioned, this is the third episode of the podcast, and if you haven't had a chance to listen to the first two, this is a great point to take a pause for the cause and go back and get a listen to those. The reason why I say that is today's episode will be a continuation of the story that I've been telling over the first two episodes. So this episode is not going to make a heck of a lot of sense if you haven't listened to the first two, because you won't understand what we're building off of. And you also won't understand why I'm telling you this story in the first place. So I would go back and do that. Come back and join us right about here at the 44-second mark. And then you can pick up where you left off. So today we're going to be talking about the Hellenistic Age. And the Hellenistic Age is actually where the Greek influence on the world will be at its highest. This is sort of the golden age of Greek culture. It actually begins after the death of Alexander the Great in 323 BC. So today we're actually going to start and kind of do a little bit of a history lesson to figure out what happened before Alexander the Great, what he did, and then why that's so important to today's story. This will also be the first of a two-part series on the Hellenistic Age, because after I got done kind of writing it all up, I realized this is much too long to be a single episode. So this will be part one. There'll be a part two coming up soon, so stay tuned for that. Now, before I begin today's episode, I do want to do Dave's Corrections Corner. The one thing I have for you, nobody sent me any major corrections. None of my friends made fun of me, so felt pretty good about that. But I did notice that the first two episodes, I was referencing an Italian school, philosophical school, as the Eleatics from Elia. While not, I guess, entirely wrong, I believe the more common pronunciation is Eleatics. So I'll probably be using that pronunciation moving forward. So I guess I hate to be that guy. Like I have heard it both ways, but it seems like with the soft E is a little bit more common. So I'm probably going to use that moving forward. And I didn't want you to be like, why the hell did he just change the way he said that word? Like, partway through the podcast. Well, if I got new knowledge, and I think that's the kind of way we should live life, right? Like if we're saying something some way, or we believe something's one way and we get better evidence to the contrary, we should probably revise our thinking rather than stubbornly sticking to the way we used to do things. So that's what I'm trying to do. So that's Dave's Corrections Corner for the day. So before I get started, I also do have to give a bit of a trigger warning. Today, we're going to be talking a lot about mathematics. In particular, we're going to be talking about the mathematics that if you're in public schools in the United States, you're probably learning in like 8th or 9th grade. So mainly talking about geometry today, a lot about geometry. Now, the good news is there's no test. I'm not going to ask you to solve any questions or write any problems down or anything like that. So don't panic. But a lot of what's going to happen over the next two episodes is going to involve math. Remember, I did say after the Platonic school of thought kind of took hold in Greece, the mathematical interpretation or an approach using mathematics to understand the universe becomes much more common. We start to see things through that lens, in large part because of the teachings of Plato and then his student Aristotle. All right, so now that all of that's out of the way, we can actually begin today's story. So like I said, we're going to be talking about the Hellenistic Age, and the Hellenistic Age begins after the death of Alexander the Great. But we haven't talked about Alexander the Great, and I think we need to do that to start. We have to set all of this up so we can understand the context in which all of this is happening, which is, I think, very important when we talk about historical things. We have to understand the context. We're going to back up a little bit more, and we're going to talk about what was going on in Greece prior to Alexander the Great, and then why that kind of help explains why he did what he did. So let's go back to our last episode. Let's talk about the time period in which Socrates and Plato were really living. So we're going back to kind of like the mid 5th century BC, so the mid 400s BC. So in order to understand kind of what was going on in Greece, we also have to understand the way Greek society was structured, kind of the way their sort of politics, okay? We have this concept that, at least I did, have this concept that Greece was sort of like this monolithic like kingdom, like the Greek Empire. But it's not really that way. What you actually have is an area of the world that is culturally Greek, but within that, you're going to have these different city-states that all have their kind of own identity and their own politics and their own perspectives on life. But they're all united by a common culture, like a common mythology, common beliefs. They're Greek, but they're also rivals with each other. So at times you would have different city-states within the Greek world kind of dominating more so over the other. And this kind of arrangement is often referred to as hegemony. Okay, so hegemony is where you have, like a first among equals kind of situation, or where one country or city-state or political entity can exert its influence over other political entities, essentially. And over time, like different city-states would rise and fall in terms of their relative power, and it might have to do with commerce or whatever. So if we go back to the mid 400s, it's really Athens that is the hegemon. Athens is sort of the dominant city-state in the Greek world. But there's another rival city-state to the south of them called Sparta that would very much like to kind of take that role over. So what you get is essentially Sparta forming a coalition of city-states that are on its side, Athens getting a collection of city-states that are its allies, and then they're going to have two wars. They're called the Peloponnesian Wars. There's the first Peloponnesian War, which happens in like around 460 BC. That is nominally won by Athens. It's not like this huge consequential victory. It's more of like Athens wins, the status quo is retained. And then there's 30 years of peace. They make a pretty lasting peace, and that works. Then we get to the second Peloponnesian War beginning in 431 BC. This is what people commonly just call the Peloponnesian War. They almost sometimes ignore the first one because it doesn't have such profound consequences. And I don't know that the history is quite as well preserved. I'm not sure about that. But technically, the second Peloponnesian War starts when, again, Sparta attacks Athens and tries to take over as the most dominant city-state in Greece. This goes on for almost 3 decades, and we did talk a bit about this. This is going on like when Socrates is kind of at his peak, and Plato is becoming his student. And it will end in a Spartan victory. So Sparta eventually overcomes Athens, and this is where we get the reign of the 30 tyrants and then the overthrow. And, a few years after that, Socrates is put to death for corrupting the young and believing in the wrong gods and all that kind of stuff. Well, this only really has the net effect of elevating Sparta above Athens, and now Sparta's the hegemon of the Greek world. But even they can't really exert that much influence over the Greek world, and their reign as like the top dog is relatively short. They get into another war with Thebes, another city-state, who defeats them at the Battle of Leuctra in 371. Athens fairly quickly regains its relatively strong political position in the Greek world, even a few short years after Sparta leaves. I mean, it's hard to replace Athens. They're this dominant maritime sea power. They have a crazy good navy, and they just have so much access to markets and stuff because of their maritime fleet that it's hard to keep them down. But we get to this position where all these different city-states are fighting for power, but it's none of those that are actually going to become the new dominant power. It turns out that's actually going to be their neighbor to the north. So if you look at the way Greece is shaped, it's kind of dangling off of southern Europe into the Mediterranean. And it looks like a series of fingers kind of extending into the Mediterranean Sea. Sparta's way at the bottom of that, and Athens is kind of like, if you're looking at the map, middle on the right, like east central part of that. Macedonia, on the other hand, is at the northern part. It's almost like the hat for Greece. It kind of blocks where Greece would connect to mainland Europe, okay? So Macedonia is actually the city-state that's going to become the dominant power in the region, and this is going to happen under the leadership of King Philip II of Macedon. He was the ruler at the time. So he kind of comes in, Macedonia kind of rises to power, and now they're the hegemon. He's kind of the top dog in Greece at this point. Again, he's not like an emperor that rules over everything, but they clearly have the most influence. And one of the things that happens now is an intellectual movement to push for a united Greece. These city-states had sort of fractured, and they've been fighting each other for the last 100 years or more to just kind of be the top dog, the first among equals, that kind of thing. But there's a problem, and the intellectuals, the smart people in Greece, see this. There's a whole other empire on the other side of the Aegean Sea. Just a few hundred years or so ago, the Persians had come in from the east. They'd swept even into mainland Greece, and it was only because all of the Greek city-states banded together as one were they able to beat them back and stop them from permanently controlling the mainland of Greece. Okay, they had done that together. And if you've seen the movie 300, you know, this is Sparta. Like, that is the story of that. Okay, but we're now forward over 100 years. And they've spent that whole period in between after that war just fighting with each other. And what the intellectuals realize is that's a recipe for disaster. Remember Asia Minor, just across the Aegean Sea? That's Persian now. The Persians have taken that over. That's no longer under Greek influence at this point. And what people begin to realize, smart people begin to realize, is that all it takes is for a fairly large, well-funded Persian army to come sweeping down into mainland Greece, and they're just going to pick off each city-state one by one because they're too busy fighting each other. So King Philip II is encouraged by these intellectuals to find a way to unite Greece again, to get them back together as sort of a solid group, even if they're individual city-states, but they're at least aligned to prevent this from happening. And the result of this is known to history as either the League of Corinth or the Hellenic League. Now, I'm pretty sure that's not what it was called at the time. I think that's a name that we've just given it, sort of posthumously through history, but don't necessarily hold me to that. So King Philip does a great job of doing this. He starts to unite the city-states back together. It's a relatively peaceful time. Philip does have to sort of like make sure that, people respect the fact that Macedonia is in charge. So King Philip of Macedon, the country is Macedonia. You may also have heard it as Macedonia with a K. I don't like that pronunciation. It sounds way too much like a nut to me. But just so you know, King Philip of Macedon, Macedonia, Macedonia, same place. It's just different names for the same place. So he does a great job of sort of overseeing all of Greece and sort of bringing these city-states back together. But he is assassinated in 336 BC by, I believe, one of his bodyguards. And then the rest of his bodyguards chased that dude down and stabbed him to death. So that was a pretty violent day. And soon his young son, relatively young, he's in his late teens, rises to power as Alexander III. Of course, he would be known to history as Alexander the Great. And the reason why is he is going to lead one of the most remarkable military campaigns in the history of the world. Okay, so a couple things happen when he takes over the throne. First, there are threats coming from the north, the Balkans and Bulgaria. They see that Macedonia is probably weak as the king has now died and been assassinated. But at the same time, he also has all these Greek city-states that his dad had united. They're now starting to go into rebellion. They're now starting to say like, oh, we see weakness in Macedonia. This is the time to like step up and maybe we can be the new hegemon of the Greek world at this point. So Alexander spends the first part of it, the first like year or so of his reign, just like telling everybody to quiet down. Like, nope, we're still in control. So he marches up, conquers the Balkans and much of modern day Bulgaria. Now his northern flank is protected. He's also basically shut the lid on any sort of invasion that could come from Persia if they want to come by land, because the whole northern portion of the Greek peninsula is now capped off by Macedonia and these other areas that he's now conquered. He then heads south into Greece and basically just reminds everybody in Greece who's actually in control. Sometimes he's got to fight. Sometimes he's just got to be like, hey, I'm that guy and you're not. So stop. So he unites all of Greece behind them. And it's not even just this loose collection. It is like he is in control of Greece. Okay. But he's not done, because he's basically now hell-bent on capturing all of the rest of the world that used to be Greek and also making sure the Persian threat is now ended. So what does he do? He sweeps down through the Levant. He goes in, takes over that whole area, moves in, captures all of Egypt. Like just Egypt, just his now. And then he heads east all the way across like modern day Turkey, captures all of that. He just keeps going through modern day Iraq, Iran. He makes it to northwestern India. Like he just keeps going and nobody can stop him. And in 12 years, he has basically come to be in possession of the known world, like the bulk of the known world. At the age of 32, he dies suddenly in 323 BC of unknown causes. And some speculate that it was an illness. Some people think it was food poisoning. Other people suspect that it was a deliberate poisoning. But upon his death at the age of 32, after this insane 12-year campaign, he is rightfully called the King of Macedonia, the Strategos Autocrator, or the military leader of Greece, the Pharaoh of Egypt, and the King of Persia. He took out everyone. Everyone. He was Michael at the end of The Godfather. I've settled all family business at the age of 32 when he passes away. It's not hard to see why he is considered to be one of, if not the greatest generals in all of history. Think about the logistics of moving an army across that much space. Like the earth wasn't smaller back then. And they did all of this in 12 years and conquered the entirety of the known world, or the bulk of it at least. But Alexander wasn't content to just have dominion over these areas of the world. He wanted them to serve as hubs of Greek influence. He wanted the world to be Greek, not that he wanted them to be part of the Greek Empire. He wanted to spread Greek culture, Greek ideas, Greek thought everywhere he went. And he built these cities and other settlements along the way to serve as these sort of hubs of Greek influence throughout this entire kingdom that he's now built. And one of the most important to history, perhaps the most important one of these settlements that he built to history, is a city known as Alexandria. It's a city that bears his name. It's Alexandria, Egypt. He built it along the Mediterranean coast, and he designed it to replace a small, older Greek colony called Naucratis that was largely the hub of influence along the Nile River Valley. So the purpose of Alexandria is to be this giant port city that is sort of this hub of Greek culture that will serve as sort of a beacon for all of the Egyptian territory. Okay? Because of its location on the coast, because of its natural sort of shape, its natural geography, Alexandria's original construction yielded two immense natural harbors. And because of its location, because of all of the factors that went into making this city, including its port, within one generation, Alexandria had surpassed the city of Carthage in size, which made it the biggest city in Africa. That is the equivalent of building a new city and 20 years later it being bigger than New York City. That's amazing. Within a century, it had become the largest city in the world. And the only city that would surpass it in terms of size and influence during the period of antiquity would be Rome, a few hundred years later. It was the home to one of the ancient wonders of the world, the Great Lighthouse of Alexandria. This great stone building had a beacon at the top, a signal fire that would allow the ships coming into these two great natural ports that had been built to not basically wreck. It made it safer, it made it faster, it made it easier for these ships to navigate this port. It would also serve as an important center of knowledge through all of antiquity and well into the Middle Ages. For centuries, it was home to the Great Library of Alexandria. This served as a repository of all existing knowledge in the world until it was accidentally destroyed by fire in 48 BC during Caesar's reign. Okay, but I don't think you can quite understand how important this great library was. The purpose of this was to be a home for all of the world's knowledge. This is basically the equivalent of Google. This is the equivalent of the internet for the world of antiquity. Because it's hard to imagine. We live in a world where everything is like easy to get access to. It's easy to find all of the knowledge in the world. But there was no repository like that, no central repository. So the Great Library was built so that they would have this sort of central collection point where all of the world's knowledge could be. Now, after its fire, there was some debate about whether the destruction of the library was partial or entire. But what we do know is, unfortunately, there are several amazing works that we will never know about because they are just lost to the ashes of history at this point. Alexandria's cultural influence would fluctuate over the centuries. So you're going to hear me talking about Alexandria more in the future. And Alexandria is still an important trade center today. I believe it's the second biggest city in Egypt. It's massive. But you're going to hear me talk a lot about Alexandria as we kind of go through these Middle Ages, and there'll be more references to it because it really sort of serves as an important cultural center and a center of knowledge for centuries to come. So, I think it's really cool that Alexander was more than just about just the bloodlust, right? Like, he was a general. He had no problem killing people when people needed to be killed. Like, it's that simple. But he also felt it was important that he was spreading knowledge and ideas and all that stuff along the way. After Alexander's death, his empire disintegrated into several Hellenistic kingdoms. So from North Africa all the way to modern day India and everywhere in between, the empire sort of fell apart. And you get these little like kingdoms run by, certain different leaders, right? So for example, Egypt becomes what we call Ptolemaic Egypt. And of course, Ptolemy is it's spelled with a P, PT. I don't know why it just can't be a T. I think that's kind of fucked up, but that's what happens all across Alexander's former kingdom. But the cool thing is all of these kingdoms would be Greek in nature. So they'll be Greek in terms of their politics. They'll be Greek in terms of their culture. And what's really cool is because the Greek world is now so big, you end up with Greek citizens or members of these Greek kingdoms coming into contact with cultures where Greek ideas had never really mixed with before. So you have Greek ideas, Greek philosophies, Greek science, Greek knowledge being spread in certain parts of Africa, being spread in certain parts of Asia where they'd never been. And at the same time, you have new knowledge coming in from Europe and Asia and Africa that the Greek world had never been exposed to. And it really shouldn't be surprising, but this is something that happens throughout history. When cultures collide, these collisions act as conduits for knowledge to be shared. And this is going to spark new ideas, right? Because you're going to get new ideas that nobody's ever heard mixing with some ideas that you've already had. And this is where you get the synthesis of new knowledge and new information. And in large part, because of this diaspora of ideas, this is why the Hellenistic period is widely regarded as the golden age of Greece. Because you're going to see a huge amount of progress be made because of these ideas blending together and being shared. So I just want you to keep that in mind, that when we get these sort of blendings of cultures, when we get these ideas being shared because of sort of this communication among cultures that have never been in communication before, this almost always spurs some sort of amazing sort of Renaissance period in the cultures where this is actually occurring, which is really cool. So like I said, the Hellenistic period is considered to be the peak of Greek influence over the world, and that's the setting for this particular chapter in our story. So in this episode, like I said, this is going to be a two-parter. In the first episode, part 1, I'm going to cover 2 individuals. And I'm going to try to give all of these Hellenistic individuals, I'm going to try to give them some sort of moniker, if you will, so that you can maybe remember them, okay? So the first one I'm going to talk to is Euclid. And I want you to remember Euclid as the geometer from parts unknown. And he's from parts unknown because we don't really know anything about him. We're not sure where he was actually born. We're not sure when he was actually born. So it's like at some point, this guy Euclid showed up. But we do know two things. One is that he flourished around 300 BC. So flourished is a term that's used to describe when someone of note is active. So like we know that Euclid was doing all of his stuff around 300 BC. So that gives us a vague idea of like when he lived. The other thing is that he spent the entirety of his career in Alexandria. So there's a reason why I introduced the city of Alexandria and told you why it's so important. A lot of what's going to happen in these next two episodes takes place in Alexandria. So the best known work that Euclid produced is called The Elements. And it's actually a compendium of 13 books. But among the other topics that are covered in The Elements, he lays out the foundations of geometry and number theory. Okay. And I know like none of these things are probably exciting you, but we got to understand like how cool this actually is in the greater context. So in The Elements, Euclid is going to do something really neat. He is going to take a bunch of mathematical principles that have existed in Greek thought for a long time. So he's going to take the work of earlier Greek mathematicians like Eudoxus, Thales, Plato, and Aristotle. He's going to take a lot of their work. But what he realizes is while these have traditionally been treated as like unique things, he sees them as parts of a whole. He recognizes that if we can weave this together, if he can weave all of these different ideas together, he can turn it into a single cogent mathematical treatise. And all he needs to do is kind of fill in the gaps to make it all make sense. So I don't want to give you the conception that like Euclid didn't do anything on his own for this book. He did a ton. But the fact that he was able to kind of like see the matrix, he was able to see like, hey, all of these things these other guys are talking about, they're all part of a whole. And if I can just sort of do some work, I can fill in these gaps and prove to the world that this is actually just like a single like mathematical field. So his genius here is that he's able to make these connections where nobody had seen them before and then he can show his work. He's going to show his work about how this all gets done. So, like I said, The Elements is a collection of 13 books. The first book is where Euclid is going to lay out what Aristotle would have referred to as first principles. He calls them postulates and common notions. We'll go through these in a little bit because they're kind of written kind of funny, and I kind of want to explain what they are. There's no test on this. You don't have to memorize them, but just listen. It's kind of neat the way he goes about this. So he is going to take an Aristotelian logical approach and apply it to math. So this is freaking neat. This is the fusion of like philosophy and math all at once. So remember, Aristotle had his first principles. First principles are things that we hold to be universally true, and then we use these first principles to arrive at second principles. Euclid takes his postulates and common notions, treats them like first principles, then does logical proofs to deduct other true information. Okay, so he's just going to do what Aristotle did. He's going to use Aristotelian logic, apply it to math, and then use deductive reasoning to find out other cool things and sort of weave these other ideas together. So here are his postulates. They're written kind of weird. So like, I'm going to give you the postulate the way it's written, and then I'm going to tell you what it actually means. So let the following be postulated. I love these mathematical things where they say that. 1, to draw a straight line from any point to any point. Okay. What he's saying there is if you put 2 points on a map, and you can always draw a straight line to connect them. Any 2 points can be connected by a straight line segment. Okay, cool. The second one, let the following be postulated. 2, to produce a finite straight line continuously in a straight line. Okay, so what this actually means is that you can take a straight line segment and extend it indefinitely in a straight line. It can go off into infinity. Then just say that. His third postulate says that to describe a circle with any center and distance. Okay, what he's saying here is that if you take a straight line segment, you hold one of the points still and then rotate the other one around it, you'll create a circle. Now, let's go back to 8th or ninth grade. If you're a Zennial like me, you had two things that you were bringing to school that year because you were doing geometry. You were bringing a protractor and a compass, and you didn't know what the difference between the two was. You know they look different, but you don't know which one was called which. So the protractor, just to help you out, that was the thing that was like a half circle, like a ruler on the bottom and an arch on top to like help you measure angles. The compass was the thing that had a really sharp pointy thing that you'd spend the whole class stabbing yourself in the middle of the hand with. And then on the other one was a pencil, and it had like a joint in the middle to make it wider or narrower. And then you would stab the pointy part into your paper and then rotate the pencil around to make perfect circles. Welcome to 8th or ninth grade. Enjoy your flashback. I don't even know if they still do that anymore. But if you're younger and you don't know what a compass and a protractor is, I don't tell you. Go Google it. You missed out on some fun. That's all he's saying, is that you can make a circle that way. You can hold the compass point in the middle, rotate the circle around it, and that essentially is a line segment being drawn around itself to create a circle. The fourth one, all right angles are equal to one another. Yeah, all right angles are 90 degrees. Now remember, he doesn't have that concept, but like still, okay. And then the fifth one, this one's a mess. I'm going to do my best. Bear with me. Okay, imagine that you have two lines, and they're drawn in such a way that the gap between them gets narrower. So like take your hands, hold them vertically in front of you, and then point your fingertips in towards each other, but don't let them touch. Those are your two lines. Now, if you were to take a line or a piece of paper and put them on top of your fingers right now, treat that as a third line. If when those lines cross that third line, the angles on the inside are acute, then at some point those two line segments will intersect with each other. That's all. Then we have common notions, and common notions are a little bit easier to understand. So, first common notion, things which are equal to the same thing are also equal to one another. Like, if A equals B and B equals C, then A equals C. Okay? That's all he's saying there. The next two, I'm going to say like a pirate, because that's the way they're written. If equals be added to equals, the wholes are equal. Okay, yeah. If I have one here and one over here, and I add two to each, now I have three of each, right? The third one is just the opposite. If equals be subtracted from equals, the remainders are equal. So if I have 3 and 3 and I subtract 2 from each, I get 1. Okay. The fourth one is things which coincide with one another are equal to one another. And the fifth one is the whole is greater than the part. Yeah, one piece of pizza is definitely less than a whole pizza. Unless you're just eating a whole pizza without cutting it because you're sad. That happens. Okay, so we're through all those. That wasn't great, but I just wanted to kind of throw it out there because I wanted you to understand how he was outlining his first principles. From the remainder of the book, what Euclid's going to do is use those proofs combined with knowledge that was provided by other people to kind of connect the dots. And the result of this is the foundations of plane geometry, solid geometry, and number theory, which are just bedrock foundations for modern math, right? These are just things that you have to have if modern math is going to exist. So while Euclid is best known for developing the math that made you dread going to school in 9th grade, he does have several other manuscripts that I'm just not going to go through in great detail that have actually survived, by the way. They still exist. So one of them concerns a mathematical theory of mirrors. It's called Catoptrics. Another one, just called Optics, covers geometrical optics. It also lays out the basic rules of perspective. And then he has another one on spherical astronomy called Phenomena. We also know he had a lot of other works. We know this because other people make reference to them or have written about them or have commented on them, but they don't exist any longer. They're just lost to time. And these are believed to focus on conics, geometric objects, and cylinders. Euclid is remembered as one of the greatest mathematicians in history. His name is almost synonymous with math. There are several fields of math that are just basically his. They're the result of his work. And while we don't know a lot about him, his work would have a huge impact on the future of math and science. To give you an idea of how impactful this work was, Elements is believed to be one of the most frequently translated and studied books in Western history, second only to the Bible. So you've got like the Bible, which was literally mandatory reading for a few hundred years in some countries. And then you also have the elements. And when scholars talk about the most impactful text to come out of ancient Greece, you've got elements on one hand, and the other one that's most commonly referenced is Aristotle's Metaphysics, which literally taught us an entirely different way to view the entire universe. So that's how important Euclid's work is. So, of course, he's one of those guys that scientists, mathematicians love to name things after. So he does have several things named in his honor. There's a crater on the moon. The European Space Agency has the Euclid spacecraft. And there's also a minor planet named after him called 4354 Euclides. Okay, so that's Euclid. The other person I want to tell you about in this episode is Archimedes. I want you to remember him as the man, the machine, the legend. Archimedes is badass. And I want you to think Leonardo da Vinci, but like 2,000 years before him. And the reason why I want you to think this is he's one of these guys that is just prolific in several different fields. He was an astronomer. He was a mathematician. He was a physicist. He was an engineer, and also made several really awesome inventions. So like that sounds a lot like Da Vinci, right? So like Leonardo da Vinci, he contributed to science both through his writings, but also through the production of new inventions, some of which were military in nature. People may not know Da Vinci developed an early plan for a tank and for a helicopter. Now, Archimedes didn't do any painting from what I can tell, where Leonardo da Vinci was also an artist, referenced the Mona Lisa and several other works of art that he did. So I'm going to go ahead and say advantage Blue Ninja Turtle over Archimedes. But stay tuned because we will be doing definitely a multi-part episode on Leonardo da Vinci because this dude is really cool and we're going to come back to him. So let's pause there on Leonardo. Let's get back to Archimedes. So like Euclid, we actually don't know a ton about his personal life. But we do know he was from the city of Syracuse. So Syracuse is a city on the island of Sicily, which is kind of off the toe of the Italian boot, hanging out in the Mediterranean. Based on an account from his life written in the 12th century by Byzantine scholar John Zetsis, which, by the way, is spelled with 2 T's, 2 Z's, 2 E's, and an S. According to John, Archimedes died in the year 212 BC at the age of 75. That would mean he would have been born around 287 BC. However, this is the account of a person that lived almost 1,500 years after the person he was writing about had died. So, I mean, we'll take that for what it's worth. So let's start with the math part and end with Archimedes' cool inventions. For the math part, I have to introduce something called the method of exhaustion. This was the mathematical precursor to calculus. So Archimedes didn't develop it. That was actually done in the 5th century by Antiphon and then kind of improved by Eudoxus and even Euclid. But this was a way of determining the volume of shapes like tetrahedrons, cylinders, and cones, where it's not quite easy to figure out what the volume is or the area of certain things are. So in modern calculus, we do this through integration. We would integrate to find these areas. They didn't have calculus. We got to wait for Newton and a few others to give us that. The way they did it instead was to basically try to fill the shape full of polygons of a known area or a known volume. And this is kind of a neat approach. So I'm going to try to explain it to you, give you some analogies to help you understand. So pretend that you have this, uniquely shaped vase and you want to know the volume of it. You can't really figure out how to do it mathematically. So what you do is you decide that, I have these little, pellets and I know the volume of every one of these pellets is a certain fixed number. So if I just fill that vase with pellets until I get to the top, and then I dump out the vase and just count how many pellets it took to fill that vase, I have a pretty good estimation of what the volume of that vase is. It's not perfect, right? Because you wouldn't be able to compensate for the little gaps in between the pellets and that kind of stuff, but it does give you a pretty good approximation of what those volumes are. Another way you can think about it, how this might work, think about when you look at images on a computer screen. we see a lot of things on computer screens as rounded or spherical, but if you really look in closely, if you really zoom in, it's actually just a cluster of polygons. But if those polygons are small enough and packed tightly enough together, our eyes give it the impression, or it gets the impression that that object is rounded, it's spherical or circular, however you want to put it. So it's kind of that same approach of using like infinitely small polygons to stack them into a space and then calculating how many of those polygons it took to fill that space. And that's going to give you an approximation of the volume or the area. Okay. I hope I kind of did that justice. But let's talk about why this is important. So Archimedes used this method of exhaustion to calculate the areas contained within parabolic regions, but the other one came down to the area of a circle. And this is why the second one's really important, because he noticed that with every circle he examined this way, there was a fixed relationship between the radius of that circle and the area of that circle. Now, I know some of you are probably scanning your brain back to like 8th or 9th grade. For me, that was a long time ago. For some of you, it might not be that long. That relationship, that constant that you have to multiply the radius by to get that area is kind of a magical mathematical number. It's pi. So if you remember, the area of a circle can be calculated by pi r squared. So you take the radius, you square it, you multiply that by that irrational number pi, that's going to give you the area. Now, pi is an irrational number. This is that one, 3.14, right? And it's the one that it just kind of goes on forever. And we've used supercomputers to calculate pi out to like the millionth or 100 millionth or billionth, decimal place. And it doesn't repeat. It goes on forever, okay? But it's like this magical mathematical number, and he figured it out using this method of exhaustion. The other cool thing with pi is that people have kind of taken up as a hobby to try to memorize as many digits, as many decimal places of pi as they can. I looked this up because I wanted to know. The current record holder for this, as of the recording of this podcast, is by Rajveer Meena, who's from India, and they memorized it out to 70,000 decimals. This happened on the 21st of March in 2015. So congratulations, Rajveer. I don't even know if I could count from 1 to 70,000 without screwing up along the way, and you remembered all of those digits. I hope you celebrate Pi Day, which is May 14th, by the way, 314. Get it. Based on extensive use of the method of exhaustion, Archimedes actually got a pretty good approximation of the value of pi. He said it lied somewhere between 3 1/7 and 3 10/71, which is between 3.1429 and 3.1408, which is remarkably close. The actual value that we know now is 3.1416. So he was pretty much equidistant on either side of that, which is really impressive. And we'll also see that other future mathematicians kind of have this goal of I'm going to do better with pi than the person before me. There'll be a competition for the accuracy of pi, as well as apparently for memorizing the length of pi. Archimedes also did something really ingenious. He was obsessed with levers and fulcrums and center of gravity. That was a big thing for him. And he famously said, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." So as part of his investigation into levers, Archimedes proved the law of the lever using geometric proofs. He used that Aristotelian approach to prove something called the law of levers. And the law of levers is really cool. So one of the concepts is something called mechanical advantage. That's basically the force multiplier you get from using some sort of lever. Okay. So basically what he figured out is that the mechanical advantage is a function of the distance between the point to which the force is applied on one side of the fulcrum and the distance to the object being acted upon on the other side. In other words, the longer the lever, the more the force gets amplified. That's why, if we said you need to give me a lever long enough and a fulcrum on which to place it and I can move the earth, because he actually found a way to mathematically calculate the mechanical advantage. And this is huge, right? So to give you an example of how this kind of can get applied, I'll go back to my time as a volunteer firefighter. So I was a volunteer firefighter for a little over a decade. As part of, learning how to do that, you have to be able to hit a fire hydrant. You have to open a hydrant and get water to a fire truck when there's a fire. And for those of you that don't know, if you look at a fire hydrant, It depends on which area you're in, but there's going to be a nut on top of that. And in order to make the water flow in through the hydrant, you have to turn that nut on top and loosen it. And it takes like over 30 turns to actually do that. It's kind of a pain in the butt. But that opens up a valve on the inside, and that allows the water to come from the water main up through the hydrant and can be fed to the fire trucks. Now, a standard hydrant wrench I think it's about 18 inches long. So it's basically a specialized wrench that goes over the top. You tighten it onto that nut, and then you use the handle, and you just wind the handle around, and that's going to open the hydrant. Now, sometimes, though, in the winter, that can freeze. That nut on top can freeze. Sometimes, because a hydrant doesn't get used regularly, it can actually sort of like rust up and be hard to open. So you can't do it. You don't have enough power with the 18-inch that you have on that handle of that hydrant wrench. So we also used to carry breaker bars, which is essentially like a 4-foot long handle extension that you just slide over the handle. So you put the hydrant wrench on, tighten it up, and then you slip this additional 4 feet of handle over it. And then you can just kind of walk around 4 feet from the hydrant and very easily open these, sort of frozen on or stuck on nuts on the top of the hydrant. Why? Because you're using the law of the lever. The longer that handle is, the more the force gets multiplied, the more power comes out of it. That's why, big wrenches have to have big handles, because if you're going to unscrew a big bolt, you better have a big handle to multiply the force. Archimedes also proved that two objects with identical masses placed on identical distances on either side of a fulcrum will balance each other. This is just teeter-tottering, right? Just picture a teeter-totter. If you put the teeter-totter together and people with equal mass are on the teeter-totter, as long as they're sitting equidistant from the fulcrum, the thing that the teeter-totters on, then they're just going to kind of float in midair, right? That's how fulcrums work. That's how scales work. This was also important for establishing the concept of center of mass, which is important for balancing objects and for his calculation of the mechanical advantage of a lever. But Archimedes is a freaking genius, and here's why. He just realized something. He realized that he could use his laws of levers and concepts of center of mass to empirically measure the area of various shapes and conic sections. Why? Here's why. Remember how I said, he found a way to sort of use this, this concept of the method of exhaustion. He basically models this in real life. So here's what I mean by this. He may not be able to find the area under a parabola mathematically, okay? Not to perfection, but he already has proven that if you balance things equidistant from a fulcrum, and they're of equal mass, that they will balance each other. So what does he do? He builds mathematical models of the problems he's trying to solve. He takes a shape of known area, of known volume, and puts it on one side of the fulcrum, then takes the one he's trying to investigate, and then he basically just balances out, basically by saying okay, if the fulcrum balances, then the volumes between these two shapes is equal. This one I can't calculate, but this one I can. And because they balance each other, I know that they're equal. This is genius. He's found a way to physically model mathematical concepts. He's also found a way to kind of leapfrog ahead and get the answer, and then use that to help calculate or help figure out how to do the calculations. Now, he writes this in a treatise to one of his friends, and we're going to meet this guy next episode. So his friend is a scholar named Eratosthenes, who's actually the head librarian at the Great Library of Alexandria. We're right back here in Alexandria again, even though he's out there on the island of Sicily in Syracuse. He writes this nice letter, and he calls it the method of mechanical theorems. There were no journals to publish this in. There was no publishing house to go to publish these things. So he just wrote it in a letter. He's like, hey, here's something I figured out how to do. Maybe this is worth being put in the Great Library. And in it, he goes through and describes this way of physically modeling what's going on, getting the answer, and then working backwards to prove his results mathematically. Why does he go through the extra step of proving his results mathematically? Because he didn't feel that the mechanical modeling was rigorous enough. He felt the need to prove things mathematically. It wasn't just enough to have the answer. He also needed to understand why it was the answer. That's amazing to me that that's his approach. And I wish that we could all take more of that approach in our everyday life. Nowadays, it is so easy to get an answer. And I don't want to say the answer. It's easy to get an answer. But it's harder to apply that critical thinking of like, well, why is this the answer? And it doesn't make sense that this is the answer. We just take things at face value so much these days because it's so easy to get that information that we never pause to go back and go, does this answer actually make sense? And that's what he's doing here. He's saying like, yeah, this is the answer I get, but does it make sense? What's the math behind that? And also, it's a great way of learning about the world. He's working backwards. He's reverse engineering the mathematics because now he knows the answer, which is really cool. And here's also something very cool about this. We knew about this document, not we, but historians knew about this document because it had been referenced before, but they didn't have the actual document. They just assumed that it had got lost with a lot of his other works. But all of a sudden, in 1906, this palimpsest turns up, and it turns out that it's actually a copy of this particular treatise written by Archimedes to Eratosthenes that shows the knowledge that he had shared with him, that basically shows how his model worked. So if that wasn't enough, if you're still not impressed enough by Archimedes, and you're like, yeah, maybe he's not Leonardo da Vinci, well, okay. He also developed the first system for representing large numbers. He wrote a book called The Sand Reckoner, which sounds like some sort of weird, like early 2000s, like, you know, independent book that would win some sort of book award. The Sand Reckoner. But in this book, he actually tries to use math to calculate the number of grains of sand that it would take to fill the universe, which I think is bold. He just says, yeah, I'm going to figure out the volume of the universe, and the polygon I'm going to use is a grain of sand. He gets a number. It's in modern annotation, it would be 8 times 10 to the 63rd, or in case you wanted to know, 8 vigintillion grains of sand. Now, I'm fairly confident, without having done any research, that there's no way to check this for accuracy. I'm fairly confident that nobody's going to be able to do that. But still, like, the cojones to try that is very impressive to me. But let's get to the cool stuff. Because in addition to being one of the greatest mathematicians to ever live, he was also a prolific inventor and engineer. So it's not surprising that if you are King Hiero II of Syracuse, it's pretty awesome that Archimedes is one of yours. Because his ability to do math, his laws of the lever, his engineering skills, his ingenuity are all very useful if you need someone to build weapons to help you win wars and help you defend your city. And it turns out they're actually going to need it because King Hiero wasn't exactly good at choosing which side of the war to be on. So one of the first things King Hiero did was commission Archimedes to craft the largest ship in existence. Just like, I want the biggest boat. And the result was the Syracusa, which is believed to be the largest ship to exist during antiquity. So he did that. And we'll talk about why he was so good with displacement and shipbuilding in just a few minutes. He also created several war machines, and these would be used in the Second Punic War. So there are 3 Punic Wars. All of them are between Carthage, that city-state in North Africa, and Rome, which is trying to sort of like grow and become more of a bully in this region of the world. All 3 of them are won by Rome. So Carthage just gets its ass kicked 3 times in a row. Some more glorious than the rest. The one we're talking about is the Second Punic War. And this one you might have actually heard of because the Carthaginian commander at the time was Hannibal. So he marched his army basically up through Spain, all the way around the Mediterranean coast of southern France, across the top of Italy, and then across the Alps and down to the boot, which goes down as one of the most remarkable, improbable military feats in the history of the world. He also does it, by the way. He doesn't just show up like with a bunch of people on feet. He's got freaking war elephants. He brought a detachment of war elephants. Yep. Elephants decked out like armored horses, but they're elephants. But despite all of this, Carthage loses this war, just like it did the First and the Third Punic Wars, with each one Carthage getting more and more diminished. But here's what happened. King Hiero II in the Second Punic War was like, we're going to roll with Carthage. So all of a sudden now Rome comes knocking at their door. So fortunately, they had Archimedes to help them. Unfortunately, they didn't win. Archimedes created improved versions of catapults. This dude's the master of the lever. You don't think he's good at making things to fling heavy objects at other people? Well, he is. He also developed a couple of different types of war cranes. One of them was a crane that just dropped heavy pieces of lead onto Roman ships. Like they would sail under it or row under it. They'd drop a big heavy hunk of lead on it. It would punch a hole in the ship, and then the ship would sink and a bunch of people would die. But the one that I think is the funniest is essentially a giant version of that claw machine that you see pretty much ubiquitously in bowling alleys, arcades, and movie theaters. This thing had a claw that would go down. It would pick the ship out of the water, raise it up in the air, and then just let it go, allowing it to smash on the surface of the water. I mean, could you imagine being one of those Roman soldiers on one of those ships? You're just rowing your ass off to get the troops onto the shore and do your attack, and all of a sudden you're just 100 feet in the air, and we're all going to die because you're just going to get dropped. I mean, what do you do with that? Like, what a wild invention. Because of his ingenuity and because of all these cool like gadgets and war machines he makes, he also gets it attributed for something that I'm fairly confident he didn't actually build. But because like this is one of those things where, and I think I mentioned this in a previous episode, some of what we hear about these people is really the stuff of legend. It's like they were remarkable people, and because they're so remarkable, it's almost believable to attribute some sort of insane invention or insane event to them. And I think this is the one for Archimedes. People sometimes say that Archimedes created an array of mirrors to focus sunlight onto Roman ships and catch them on fire. They call it Archimedes' heat ray. Now, most people, most historians do not believe this is real. But could you imagine? Could you imagine you're just sailing along or, rowing your trireme along, and then all of a sudden, like a giant magnifying glass to a giant ant, your ship just gets cooked and starts on fire? I mean, that would be wild. I don't think it ever happened, but how cool would that be? Now, unfortunately, Archimedes dies during the siege of Syracuse. The Romans knew who Archimedes was. They knew how important he was, how brilliant he was, and they knew that Archimedes was worth much more alive than dead. Nobody wanted to hurt Archimedes. And the Roman soldiers, the Roman commander was like, if you see this guy, don't hurt him. We want him. He's an asset. Unfortunately, the Roman soldier who confronted Archimedes while he was doing calculations in the sand didn't know who he was. And when the Roman soldier was like, dude, stop doing that, and he was like, no, I'm going to keep doing this. This is too important. The Roman soldier got pissed off and just killed him. And according to one Roman account of the event, as he's laying there, like just dying, he actually tries to cover up the figures he's drawing in the sand, and he begged the soldier to please not disturb his circle. So he ends up dying despite that wasn't the intention. Now I'm going to end this episode and our conversation about Archimedes with one final story. And this is the one that you probably know about him. You might not even know that it was Archimedes. You've heard this story. I feel confident in that. It's the story of the Golden Crown, sometimes called the story of the Golden Wreath. But either way, it's the tale about King Hiero, who commissioned a craftsman to make a golden crown out of a solid chunk of gold. So he gave him like a nugget of gold of a set weight and said, I want you to take this, melt it down, and fashion it into a golden crown. And this is very important because it's the crown that he's going to wear as the king. It's also important because I think it's going to be used in some sort of religious ceremony, like an offering to the gods and that kind of stuff. So it has to be done right. Okay. So he gives this to the craftsman. The craftsman comes back, gives him the crown as ordered. But then the king starts to hear rumors that perhaps the craftsman wasn't exactly honest. And while the crown looks golden, it's actually not pure gold. The craftsman had taken some of the gold and then replaced it with silver. But because the crown had the right weight, it was really impossible to tell whether or not that was true. So King Hiero II goes to Archimedes and says, hey, look, I think this guy scammed me. I think I gave him a chunk of gold, said very clearly, I said, use all of this gold and make a crown, and I better get all the gold back in the form of a crown. And now I'm being told that this might have like some silver in it, and like that's not cool, and I need you to figure out whether or not this is true. Because like he didn't want to like, credit to the king. He didn't want to just call this dude out. But like, remember, this is important for like his reign. It's important to the gods. So if he tries to present this as like an offering to the gods and it's not like 100% pure gold, I mean, that could lead to untold damage. So Archimedes is like, yeah, I'll try to figure this out. So this is a big like thought experiment for Archimedes to figure out how he can parse this apart. So there's two versions of the story. Okay. But I'm going to tell you the good one first, and then tell you what probably really happened later on because it's not as fun. The original story is the bathtub story. Archimedes was thinking about how he would be able to sort of disentangle this. How is he going to determine whether that crown is entirely made of gold or whether there's some sort of, fusion of gold and silver, amalgamated together in this? And as he's thinking about this, apparently at some point he went to go take a bath. Probably to relax and just, unwind and let his mind kind of think about this. Now, back then, you don't have a bathtub in your house. You have to go to the public bath. So apparently he's in the public bath, slides, into the bathtub, and he realizes, like, when he gets into the bathtub, the water level rises. That's where the water splashes out. That he displaces that water with his mass. And he has this epiphany. And it's in this moment that he sort of understands what will become known as Archimedes' principle, which states that the upward buoyant force exerted on a body immersed in a fluid is equal to the weight of the fluid it displaces. So what he's understanding in this moment is that a lump of gold that weighs the same amount as a lump of silver will displace different amounts of water. And he finally realizes that this is the answer to the question that he's been asked to answer. And he shoots up out of his bathtub, doesn't put any clothes on, runs out of the bathhouse into the streets of Syracuse, buck naked, dripping wet, screaming, "Eureka, Eureka, I found it." He's now figured it out. And that's why I put Eureka in the title of this episode. Because what he experiences in this moment is something that I think we've all experienced in our life. It's that moment of that epiphany where all of a sudden you're like, that's it. I get it. Where all of a sudden those puzzle pieces all just connect suddenly. And you're just like, oh my God, it makes sense now. So he's running buck naked through the city of Syracuse because he's figured out how he's going to be able to figure out whether this crown is purely made of gold or whether it's some sort of amalgamation of gold and silver. And the way he does this is by taking a lump of gold that weighs the same amount of the crown and a lump of silver that weighs the same amount of the crown as the crown and putting them in water and realizing that they're going to displace different amounts of water. But if the crown is made entirely of gold, it will displace the same amount of water as that lump of gold. But if it's a mixture of gold and silver, it will displace some sort of intermediate amount of water between the lump of gold and the lump of silver, and that's what happens. And when they place the wreath in the water, all of a sudden, the crown in the water, all of a sudden, it's revealed that that crown is not made entirely of gold because it didn't displace the same amount of water as the lump of gold did. Now, that's the legendary tale. It's also very likely that rather than just sort of submerging them in water, he used something called a hydrostatic balance or a submerged balance. And basically what he did is he places a balance underwater and places gold on one half of the scale on the balance. And then he puts either silver or the wreath on the other side of the scale. And neither one of them is going to match the weight of the gold. We think this is probably how it likely happened. And there's a couple reasons for this. First off, Archimedes published a technique in which he described how to do this in a book called On Floating Bodies. And then Galileo would make reference to this when he reinvented the hydrostatic balance in the 1500s. And we'll get to Galileo at some point too. That guy's a complete rock star. But this principle of displacement, now known as Archimedes' principle, is one of the founding principles of the field of hydrostatics. So Archimedes is a pretty impressive individual in terms of like I can hardly get through all of them. I could probably do a whole episode on each one of these guys, but I mean, who has the time? Maybe we'll come back at some point in the future. So Archimedes, great inventor, fantastic mathematician, really just a genius in the way he can, sort of use both physical and mathematical modeling as well as just sheer mathematics to do some pretty amazing things. Not to be outdone by Euclid, Archimedes also has several namesakes. You may have heard of something called the Archimedean screw. This was something that was used on ships. So the world's first seagoing steamship with a screw propeller was called the SS Archimedes. He's got a lunar crater and an entire lunar mountain range called Montes Archimedes on the moon up there, named after him. And then we also know that the state of California's motto is Eureka. I found it. Now, Archimedes was saying Eureka because he just discovered essentially the concept of displacement, whereas California's Eureka is I found it, and what they're talking about is gold. So, this is the same, but also different. So I'm going to stop here. We're over an hour in. I think we did a pretty good job sort of describing where we're at historically. We got to meet Euclid. We got to meet Archimedes. I've got several very cool individuals to introduce you to next week, including a guy that's going to pretty remarkably estimate the size of the Earth, like in the 200s BC. So like that's going to happen next episode. So plug for that. Come back for that. There's going to be some cool stuff. We'll also learn about Eratosthenes. So Archimedes' like little best friend in writing and pen pal. We'll learn about him. So that's coming up in the next episode. As I wrap this one up, I just want to say that I truly appreciate every one of you who listens to this. Good for you for taking time to sort of learn more about the world, to just gain new knowledge. I'm hoping that you're finding these entertaining, but I'm always open for suggestions. Send me ideas about things that you want to hear about on the podcast. If there's things that I'm doing well, tell me. If there's things I'm not doing well, tell me, but be gentle. I don't want to eat a whole pizza by myself because I'm sad. And then I appreciate all the positive feedback that I've been getting. If you want to reach out to me, thatbiodoc@gmail.com. I do have my YouTube page, thatbiodoc, on YouTube. You can also see my other science instructional videos on there if you want to look at those. That's also one of the places where I post this podcast. So maybe you're watching on there already. But I really appreciate all of you out there who are listening to me, and I can't wait to talk to you again. So I will talk to you again when the next episode comes out in a week or two. And thank you so much, and I will talk to you soon. Bye.